to see this class. We don't want to see the recording of this class. But we can wait. We can wait till you get home to review chapter number 12. Anybody else have a problem they would like to work on, to look at? Trying to remember what some of the questions are. This chapter. Yes. This is an example that came almost directly out of the book. This one's this one is commonly missed in this class. I often have people with questions about this problem. Did anybody get to do this problem with the multiple cannons at different heights and different speeds and so on?
I think I left off on that one, so I haven't done that one either.
So in this problem, they want to know, we're going to rank these cannons from farthest to shortest horizontal distance traveled before hitting the ground. And the best way to do this problem is to solve for the horizontal distance as a function of the height and a function of the initial velocity. Do it symbolically. That way you have a formula that you can just plug in the numbers and get all the numbers out. You could try to figure it out just by kind of guesstimating, but it's not easy to do. So in fact, I don't think I've ever had anybody that's succeeded in doing it that way. So let me show you what this will look like. Let me see, get my, there we go. My drawing is going to be a little bit, well, actually, I think my mouse might be charged. If my mouse is charged, it'll make it a little bit easier. Go a little bit better. Let's see if it's working. Looks like it's working. That's good. That'll make my writing a little bit smoother. Okay, so what we've got here, the things that we know in each problem is we know that we'll call the final height 0. So we'll say that y is equal to 0 at the end. We'll say that y initial is equal to whatever height we are given. We'll just call it h, and that's this height here, whatever that is. We also know, and we also know that in the vertical direction we're going to be using for our acceleration, we'll be using negative g or whatever. And that's all we really know in the vertical direction, but that's enough. Oh no, there's one more thing that we also know in the vertical direction. We also know that the initial velocity in the y direction is 0 because it's only moving horizontally at first, and then it starts to accelerate downward. So initial velocity in the y direction, we know the final y position, we know the initial y position, and we know the acceleration, and that's all in the y direction. In the x direction, we know the initial velocity in the x direction. That's terrible. That says v0x, I don't know, but it's supposed to say that. We know that is whatever velocity they give us here, this one here. We know that the final velocity is going to be the same because it's not going to be affected by, there's no air resistance, so it's not going to change. That means the acceleration is 0, in other words, in the x direction, acceleration in the x direction. And we're also going to say that the initial position in the x direction is 0 because we're trying to find the final position in each case. This is the thing we're trying to find. All right. Now the equation to find this final position is really quite simple. The equation for that in the end looks like this. It looks like x final equals x initial, which is 0, of course, plus velocity in the x times time. The problem is that we don't know the time. The time is dependent on how long it takes to fall through each one of these, right? So we need to solve for the time. So we go and we use this stuff to solve for the time. We have a couple of different equations that we might use that have time in them, and the things that we've got up here possibly. Let's take a look at our kinematic equations. One of the kinematic equations we have is that the final velocity in the y direction equals the initial velocity in the y direction plus acceleration times time. Acceleration in the y direction times time. Problem is we don't know what our final velocity is in the y direction, so that's maybe not the best equation to use. We also have initial or final position in y equals initial position in y plus initial velocity in y, which is 0, times time, plus the acceleration in y, which is the negative g, times 1/2, didn't put the 1/2 in there, times t squared. Now this one is good because we happen to know the acceleration in the y direction, that's negative g. This actually is 0 because we're saying that our initial velocity in the y direction is 0. And we know our initial position is 0 and our final position is y, is that height that we go through. So we can actually figure this part out. This part, we can actually use this equation to calculate t. So let's go ahead and do that. We'll do it symbolically. We'll do this by dividing each side by the g. So we're going to take y divided by g, which is our acceleration. Multiply both sides by 2, and then take the square root of both sides. So this should tell us the time that it takes each of these cannonballs to fall to the ground. And then we should be able to plug this into here with our velocity, and this being 0, and solve for x. So our formula in x looks like this. X equals velocity in the x direction times the square root of 2 times, now instead of using y, we'll use the height here. We'll just, because our y is equal to the height, 2 times the height over g. And now you should be able to figure out which one of these goes the furthest distance just by plugging in this for your velocity and this for your height, and this for your velocity and this for your height. Do that to every single one of them. You should be able to figure out how far the cannonballs go and then rank them in order. So this is a classic example of using kinematic equations to create a formula symbolically, and then you just plug it in again and again and again to get your answers. Any questions about what we did there? Okay. Are we ready to do number 12 yet?
Yes, sir. I'm loading up Zoom right now.
All right. Let's move to number 12 and see what we can see here. The ball is launched from the ground at an angle with a velocity of 35 meters per second. What angle should they throw it at to travel the furthest distance? All right. Where during its flight is its speed the least? At what speed will it hit the ground? Well, it's good. So we'll start by drawing a picture. So here's our picture up here. We're going to launch this ball. This is going to represent its initial velocity as a vector. And it's going to have some angle, theta. And we know that the velocity initial is 35 degrees. It's not 35 degrees, but 35 meters per second. We might as well write that in so you know that we know that. Remember that we know that. And they want to know where during its flight is its speed the least Now, what speed will it hit the ground? Remember that speed is the absolute value or the magnitude of the velocity. Excuse me. It's the numerical value of the velocity vector. So we do know a couple of things. First of all, we know that we know from the last chapter when we threw the rock up and then it came down on the cliff at the edge of the cliff kind of thing, right? We know that when we did that problem, that that there was this symmetry of the upward movement versus the downward movement. In other words, if we track this ball as it goes through the air, till it hits the ground over here, and we split this motion directly in half, as long as there's no friction involved, and here they've not said there's any friction involved, so we can assume that there isn't. The symmetry goes like this, that the upward velocities, the upward component of the velocity, remember that at each point there's a velocity vector, and that velocity vector can be broken into two components, an x component down here, which would be your velocity initial in the x direction for this particular one, and this would be velocity initial in the y direction. But the y direction velocities, when you're in the gravitational field, will get smaller and smaller and smaller until you get up here and then they stop. There won't be any y direction velocity up here. Vy equals 0 up here. And then they'll increase back again, and their increase will mirror the decrease going up this way. So as the vertical velocity vectors, vertical velocity components got smaller and smaller and smaller to 0, then they get a little bit bigger and bigger and bigger back to where they were at this point, down at this side. But on this side, instead of being up, it'll be down. But when the thing lands, it'll have the same downward velocity as this one had upward velocity on this side. So there's that symmetry. So we can use that symmetry to take advantage of a couple of things. Particularly, we can use that symmetry to take advantage of this answer right here and this answer right here. Where during its flight will its speed be the least? So what is the answer going to be for that one? The way that you think about this is you think, well, the overall speed is the magnitude of the velocity. The magnitude of the velocity here is 35 meters per second, and the direction is at some angle theta. But this 35 meters per second is, part of it is in horizontal, part of it is in vertical. The vertical is decreasing, 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 but the horizontal is staying the same amount. This horizontal movement is some amount of velocity that is less than 35, but when we add the y portion to it, we get 35 total when we start. So where in this movement are we going to get the least amount of speed?
Does it count when it hits the ground?
No, it's because we're not going to talk about when it hits the ground. It's only going to be right before it hits the ground, right? Right when it hits the ground, there's all kinds of accelerations and things like that that we don't want to mess with. So we're not going to talk about when it hits the ground. That's not allowed. But somewhere during this moment, I mean, think about it in terms of just your experience. When you're experiencing throwing something up in the air, where does it appear to have the lowest amount of speed?
At the top.
At the top. And that's actually pretty good intuition because it is at the top. Even if you're throwing it forward, even if it's like Tom Brady throwing a 60-yard touchdown pass, right in the middle of that throw, right when it's at its peak, the ball is actually going the slowest, and then it's going to speed up again as it falls back down towards the person catching it, right? Because gravity is going to speed it up in the vertical direction, and that vertical direction plus the horizontal direction is going to give us an angled velocity down towards the player catching the ball. So the place that is slowed down the most, or it has the least speed, is at the top of the motion. Now, what speed will it hit the ground with? This is another thing that we can actually take from the symmetry. We start off at 35 meters per second, and then we slowly slow down as we lose vertical velocity till we are at our slowest up here. We're not at zero speed here because we're still moving forward. We're just not moving up or down. But then it starts to fall down again, so it speeds up and the velocity increases as well. And then we get down to what velocity down at this end, or what speed rather. What's the magnitude of our velocity according to this symmetry thing? Remembering that the word symmetry comes from the same, which is not a pun, not intended to be a pun, but the same prefix is the word same, right?
Would still be 35.
It would still be 35. It's 35 meters per second right as it hits the ground, because right as it leaves the ground, it's 35. And the only thing changing the speed is going to slow it down and then speed it back up again to its original speed in that vertical direction. So we can just write down those last two answers, and the only one we have to do is to figure out this first one. Now we can figure out the first one kind of from symmetry, but it's not a really good method because most of us don't know enough geometry to truly do it that way. But we can do it using mathematics in a fairly straightforward manner. If we're trying to go as far as we possibly can go, then we're looking for distance in the x direction. Well, what do we know about this thing? This thing here, we've got initial velocity in the x direction. We've got final velocity in the x direction. We know those are both the same velocity. So it's just like that previous problem that we just did, where the position final rather is equal to the position initial, which we'll call 0. We'll just call where he throws from 0, plus the velocity in the x direction times time. And we know the velocity in the x direction, we just don't know the time again. So we've got the same issue here, we're just not sure about the time. Well, just like the previous problem, we can actually calculate the time by using this equation here, where we have our final y equals our initial y plus 1/2, or sorry, gotta undo that, plus velocity initial in the y direction times time, plus 1/2 at squared, where a is equal to negative 9.8 meters per second squared. Well, this time our initial y can be 0. We can say that our initial height is 0. We can call this height right here 0 if we want to. That's great because that gets rid of that term. But the problem is that we don't know, we do know our initial velocity. Our initial velocity we can calculate. This right here, our initial velocity in the y direction is going to be equal to the velocity initial, which is 35 meters per second right there, times the sine of our angle theta. So we can figure out that thing right there. That's fine. The problem is we don't know the actual final height. The final height in this problem is going to be a little bit of a mess. We don't know what that is. So we maybe want to look at something else. Maybe we look at initial velocity and final velocity in the y direction. Initial velocity, final velocity in the y direction. We do actually know those. Plus acceleration in the y direction times time. This one will be a little bit easier to solve because we know the acceleration in the y direction, we know the initial velocity in the y direction, and we know the final velocity in the y direction because we've already figured that out in these second two parts. So this would be a great one to figure out what the time is, and then we can use that time in the x equation up here to calculate the distance that we're going to go in the x. So let's solve this bottom equation for time. This bottom equation for time is going to be time equals, I'm going to be taking the velocity in the y direction final and subtracting the velocity in the y direction initial. And then I'm going to have this thing that I'm going to have to divide out on both sides, which is g. I'm just going to divide by g there. So the time will be the difference between the initial and final velocities in the y direction divided by g. Well, the velocity in the y direction, finally, the final velocity in the y direction is this one up here. And this one up here is going to be negative v naught sine theta. And then this one over here, if I subtract the initial one, that's a plus v naught sine theta. So I subtract plus v naught sine theta. So I subtract v naught sine theta again. And that's all over g. And it's actually, g is negative 9.8. So the negatives end up going away. We'll put a 9.8 down here. And we'll put a negative 9 out here. Then we'll change all of these negatives to positives, because we'll multiply the top and the bottom by -1. And that'll make it easier. That makes this equation look like this. 2 times v naught over g times the sine of theta. That's what the time is. The time is 2 times v naught g sine theta. Now our equation for the distance is x equals x naught, which is 0, velocity in the x times time. The time is 2, I'm going to put the 2 out in front, times the velocity. This is the velocity initial in the y. This is velocity initial in the x. It's just velocity in the x. So velocity initial in the y, all over g. Now all these numbers stay the same. None of these numbers change. The thing that does change is the theta. That we're trying to figure out what is going to give us the biggest number for x if we change theta. Well, when does this number well, actually what we want to do is, let's see, what are they wanting to do? What angle should they throw it at to travel the farthest distance? Right, did we get that right? I think that we've actually, I think I made a mistake here. Did anyone see me make a mistake? I'm trying to see if I made a mistake. I'm pretty sure that I did, because this doesn't seem correct to me. Uh, let's see, V naught, Vy, that's correct. That's correct. That's correct. This is, I've made a mistake here and I can't find it. And obviously nobody else found my mistake either. This is correct. Oops. Oh, where's my mistake? I can't find it.
Is it because v in the y direction equals 0? So doesn't that disappear?
No, I'm going from here to here for the total time. I'm calculating the total time going from this point all the way to this point. So the initial velocity is up at v naught sine theta. The final velocity is down at v naught sine theta negative v naught sine theta. So this should end up being final minus initial. Final minus initial. The final is negative. The initial is positive, so you should get a negative minus a negative, or negative v naught minus v naught again, both times sine theta.
Yeah, that makes sense. Does it matter that the sign at the bottom isn't being divided by gravity? Because shouldn't it be right there?
It still is because I've divided it over here. So you can divide it here or you can divide it here. It doesn't matter one way or the other. The error is inside the sign for some reason, and I'm trying to remember where that comes into play. I'm just not remembering what I did. This should end up looking like something constant times the sine of 2 theta. Because the answer should be when this is when this gets the biggest, this is at its biggest, because the only thing that's changing is the sign here. And when this is at its biggest, the sine of theta is at its largest value when the sine is equal to 1, and the sine is equal to 1 when the argument inside the sine is equal to 90. Right. And so it should be 2 theta equals 90, and theta equals 45. And I'm trying to remember if that has something to do with something that you have to do in calculus, but I don't think it is. I can't remember the last time I've actually worked this problem, so I can't remember if I had to do it with calculus before or not. But I don't think so. I think there's something that I did wrong using this equation rather than this one, maybe. If, let's see, this is velocity final equals velocity initial plus acceleration time. This should be correct. And if we're going from here to here, then those two should be the same velocity but different signs. One up, the final one, no, the initial one up, and the final one down. As far as I can tell, that is all correct. Because I seem to remember when I've done this before, I ended up having to have, I seem to remember ending up with a times squared, which gave me a sine squared, which meant that I had to use some kind of identity formula to turn a sine squared into a sine 2 theta. And then that became this. But of course, that violates my rule of not using trigonometric identities that I promised you about that we wouldn't use. But anyway, I seem to remember there being something like that. So I'm trying to think if that is why I'm thinking of this particular equation instead. because that would bring in the time squared, which would give me a sine squared, which would give me a sine 2 theta. I can't see why this one wouldn't be allowed to be used, but it's possible that I'm just overlooking something. There are a lot of things to overlook. I don't want to waste too much time just sitting here trying to find my error. So what I'm going to do is I'll go ahead and look at this later and check to see if I can figure out what my error is on my own and then get back to you all on that. And in the meantime, I'm going to show you the other version of solving this problem, which is technically, most people would say it's easier. And you'll probably think it's easier once I show it to you. But most people, while they might be able to point out that this is true, they won't be able to tell you why it's true. But this is the reason why it's true. We know that that these two vectors here are the components of the initial velocity vector, and that this vector here is equal to v naught cosine theta, and this one's equal to v sine theta. Since at the end we're still going the same velocity in the x direction, we know that that component in the x direction is the same as this one. But we also said earlier that it's going to be going down at the same speed here at the end as it was going up at this end. So we know that this length and this length are the same. In other words, these two triangles are the same triangle. They're congruent triangles, I guess we could say. They're congruent triangles. Is that the word they use, or do they use? Yeah, I think they use congruent triangles. But that means that the lengths of their sides are the same and that their angles are the same. And that means that just by Pythagorean's theorem, we can say that the velocity here is equal to the velocity here, which gives us this last answer for the speed, in fact. And we also can say that since they have the same angles, that this angle over here will equal this angle over here. Actually, that's not the question they're asking, so that doesn't matter. But anyway, the point being is that the thing that we're trying to answer is what angle should we throw it at to get it the furthest? Excuse me. And so what we can do is we can actually say, well, we can do one of two things. We can actually do a trial by experiment. We can actually calculate the distance at different angles. And if we do that, what we'll find is that once we get to 45, we're going some particular distance, and we go over 45 and we start going less distance again. So we go further and further and further from 0 to 45, and then from 45 on, we come back closer and closer and closer to where we launched from. And that's something that we saw in the experiment that we did, the virtual experiment we did with the cannonball pianos the other day. But we can also do that through similar triangles. You can actually build similar triangles side by side and essentially calculate the length of their sides, because as this elevates more and more and more, this velocity down here gets less and less and less and less. And if you once you get to 45, you've essentially reached the halfway point for the velocity in the x direction. And since it has to do that on the way down as well, then your maximum has to be at 45 degrees. If you go less than that, you're going to hit the ground early. If you go more than that, you're going to hit the ground later. It's going to take longer. It's going to go longer in the air, but you're going to actually hit the ground at a closer spot. So it does come down to a couple of different ways to do it geometry-wise and using the symmetries, or using the experiment. You can do it that way. So those are all kind of more intuitive things. Geometry being a very intuitive mathematical thing, and the experiment, of course, being intuitive because you're actually doing the experiment. But not necessarily easy to prove for most people. And so most people don't necessarily go that route. And I will get back to you on this because I don't want to just spend lots of time. Obviously, I can't see the mistake I made, so I'm going to turn away from it for a little bit and come back to it later and try to figure out where my mistake is. And then I'll get back to you on that. I'll either post a video about it or I'll tell you. I'll probably post a video since today is Wednesday and we're not going to see each other until next Monday. So, okay. Anybody have any other questions about this problem? Anything that they want to ask about this, except for this part here that I'm still thinking about? Yeah. Okay, what other questions might we have about other problems in the homework?
Good besides those two.
You're good besides those two?
Yep.
All right. Anybody else? Anybody else have questions? Trying to remember all the questions that are in here. Oh, here's another one that people love. Anybody do this problem? Anybody get this problem with the car going off the table?
Yeah, it took a lot of time.
Yeah, this one's a lot of fun. This one does take a lot of time. But this one is very similar to the cannon problem with different heights of table, except that it also has a length of the table that it's accelerating. So you have to use kinematic equations in the x direction to calculate how fast it's going by the time it gets to the end of the table. Once you've done that, so first of all, you're calculating the acceleration from a kinematic equation. Then you're going to calculate the velocity at the end of the table. Then you're going to calculate the time that it takes. Then they're going to say we're going to put a ramp on the end of the table. So now it's going to be going this velocity here in this part B. It's going to be going that fast, but it's now going to be going at this angle off the end of the table. So then you have to break this vector into two components using this velocity for the total velocity, whatever you calculate in part B, for the total velocity here, and then getting two components for that velocity in the horizontal and vertical directions. And then you'll write those down. And then you're going to actually, in the y direction, you're going to determine from the initial y component of the velocity and the height of the table, you're going to figure out how long it takes for it to hit the ground. Then once you figure out how long it takes to hit the ground, you'll figure out how far it goes in x using the x final equals x initial plus velocity in x times t. And then you'll add that distance to the original distance along the edge of the table, 1.9 meters, to get the very last answer, and then you're done. No, sorry. The very last answer is actually trickier than that now that I'm looking at it more closely. The very last answer, you actually have to realize that you're starting from here and you're going all the way to here. And this is the displacement vector that you have to calculate. You have to calculate the length of this vector, and I believe they want you to calculate the angle of that vector as well. No, yeah, but they don't want you to calculate the angle, they just want you to show the direction. So the direction is obviously this one, since it's pointing downward to the right, but you do need to figure out the length of this one. And to figure out the length of that one, you have to realize that one side of this triangle that makes up this whole vector, so this vector has two components. It has an x component that looks like this. And that one you just add the 1.9 meters to the to however far you've calculated this car is going to go in the x direction in this part. And then the height of the table is this one. And then you can use the Pythagorean theorem to calculate the length of this vector. And that's how you do that problem. It is certainly not just, easy to do or quick to do. This is a problem that has a lot of different calculations. You have to get every one of them right to get the next one right, and so on and so forth. So be very careful and be very methodical in how you do this problem. And this problem,
I have a question.
Go ahead.
Not exactly pertaining to this problem in particular, but say I find the acceleration and I want to check it. Can I submit and still have like 7 tries for the next few? Because that's what it kind of seemed like while I was going through it.
I think that's the case. Yeah, I think it is. I think that it does count part by part your number of tries. I believe so. And if it doesn't, it's not that big a deal. If you need a couple of extra tries, just just tell me. I'll fix that. It's easy to do.
Okay, makes sense. Again, I think it was working that way, but yeah, I just wasn't sure.
Okay. So does anybody else have any questions about this problem? Because this one is a little bit challenging, takes time and some effort to get through it. All right, and one more time, any other questions? Okay, I am going to stop sharing my screen for a second here. I'm going to just take a look and see where everybody is at on the homework so I can decide what to do with the rest of our time today. So it looks like we've got a couple of people that are fairly well along, and then some people that have not gotten very far along in the homework. So what I'm going to do for today, since we're in a pretty good place as far as getting through chapters so far, what we'll do is we will go ahead and let you take the rest of the week to work on the homework, the rest of the day today to work on the homework, to get your lab work done. Maybe maybe you could even get another, maybe you can even move on to the next lab in the sequence. We'll take a look at that really quick. But instead of trying to move on to chapter 4 when people are still working on chapter 3, that has a tendency to really frustrate students' progress. So I don't want to get ahead of where people are in the homework too much. So let's go ahead and go to the IO lab stuff here. Wow, the internet is slow right now. To be expected, I suppose. Okay, let's see if I can open up IO Lab stuff. It is not working properly. Nothing's working properly. Looks like. Oh, there we go. Finally got to it. Okay. So let me share my screen again here. Suppose I could have just clicked in math, but I didn't. Okay, so the first one that we did is this one here, which is, no, that's not the right one, sorry. It was this one. This is the first one that I didn't want to download it, I just want to open it. There we go. So this one here, which is kind of a, just learning how to use your IO lab, setting it up and so on and so forth. Again, I don't want to download it, I just want to look at it. Here we go. So you're collecting some data, you're just doing some different things, graphing some things, It's not that big a deal, and you're pretty much doing the same things just by watching those videos that I told you about. But in lab 2, you're actually going to do some experiments. And so this would be the next thing. Just go on to lab 2 and open up the lab 2 activity. You can also look at any of the slides, the PowerPoint slides, or anything you want to. Any of this stuff is fine to look at if you'd like, but lab 2 activity will tell you what needs to be done. In this one, you're going to create a little ramp. I suggest, using like I don't know, a board or some kind of something that you have that's big enough to slide the car up and down, stacked on with a couple books on one end or something. You can also lift a table up on one end and slide the car up and down a slanted table. Whatever you end up doing, this is the basis of this experiment, where you're going to push it up and let it fall back down, and that all of a sudden becomes an acceleration in 2 dimensions, right? So you've got now a 2-dimensional acceleration experiment, and they talk about the different things that you'll measure, the different things that you'll be making graphs of, and so on and so forth. You're going to be doing some averaging, so they're going to talk about the averaging tool in the IOLab software. And it is, again, fairly self-explanatory. It's not too difficult to use. And I do believe that they actually have some videos for this one as well. Let's take a look and see what we've got here. Some videos that are related to this somewhat, I think. Let's two activity.
This is Kyle. He invented one
Hi,
way
Kyle.
to destroy boredom.
Enough, Kyle. Okay.
Let's select our sensors. Give it another little push.
Oh, they're doing a little bit simpler lab
There we
here,
go.
so.
And go back to analysis mode.
Let's see here. These ones, they are using slightly different experiments in these videos, but trying to find one that looks like what we're doing here.
Okay, I'm just going to pull back on this.
No, this one's different too. So that one's actually our next lab, that one. But anyway, I don't see a video in here for this, but it's not a terribly difficult experiment. I didn't have anybody have any troubles with it. But if you do have any troubles with it, please feel free to ask questions. So going back to lab 2, for any of these experiments, you can literally just take these documents, since they're also in a docx form, a doc form. Open up a Microsoft Word, and you can just kind of add some things in here if you want to. You can, for example, you could actually just take each one of these things here and just fill it in with a paragraph of your own or whatever, or just list or your just put your graphs in it if you want to, just to make things a little bit simpler on how to turn in your work, quote unquote. Just show me that you've actually done some experimentation. And again, I would like you to do some experimentation. For example, in this one, if they're pushing the car up the hill and letting it come down, well, what would happen if you just held the car at the top of the hill and let it go? Or if you pushed it on a flat table like we saw in that video just shortly, or anything else, find some different things that are maybe of interest to you. Maybe you have a half pipe at your house for your skateboard, and you can have it go up and down, back and forth, or maybe in a bathtub or something. Whatever, just try some things out to try to explore the ideas of 2-dimensional acceleration, two-dimensional velocities, 2-dimensional displacements, and even or even 1-dimensional stuff. 1-dimensional kinematics is fine too, since we got through that chapter. So spend some time exploring some things, write down what you explored, what you did, give me some data, do some analysis of it to show that you've, calculated that, these things kind of perform the way that you thought you did. showing me that you've learned some things once again. And so, and this is of course the next lab. So if you don't have time for it this week, that's fine. We'll finish it up next week. But if you do, you can go ahead and do it and have something else to occupy your time. Now, is there anything else, anything that anybody has any questions about before we finish up for the day and turn you loose on your homework and your labs and the rest of your week?
I'm good.
No other questions? Nobody else has anything? All right. Well, if nobody else has anything, I'm going to go ahead and sign off. Feel free to email me and call me and whatever you need to as you're working on your homework and labs and everything else. And then we will be ready to start chapter 4 on Monday. I probably will not take a whole lot of time to work through homework problems Monday before class, because it will be a lot to get through chapter 4 in one class, but I still want to try and see if we can. So if we absolutely must, we will, but try to get your questions into me before the weekend so that I can answer them and you can get the homework done. When is the homework due? I didn't check that.
On Friday.
It's due on Friday? Okay. I should probably not do this. Goodness gracious, all my things are open to grade books. It's a class you're not in, so it doesn't matter. Okay. So let's change the, let's maybe make it due the end of the weekend or something. Give you a couple extra days. I'm going to give you a couple extra days on this. You should be aware though that I do not answer emails on Sundays. I take Sunday off completely. And I usually do try to answer emails on Saturdays, but I might go to bed a little early on a Saturday, and I might be in and out on a Saturday, so I don't usually answer them as much. But I definitely do not answer emails on Sundays. So make sure you get all your emails to me probably by Thursday or Friday, so that I can have some time to answer them and get back to you before you finish up your homework this weekend. And with that, I'm going to bid you farewell. Looks like we've not had any bad weather, at least in my end of town yet, but hopefully we won't have any. And I hope you all have a good evening and a safe evening, and we'll see you next week.
See you, sir. Have a good weekend.
Thank you. You too.